get started here. See, you already got the button. La, la, la. All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class, and I just pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so I want to talk more about differential forms, just kind of complete the thought of yesterday. I told you guys I should talk about, other non-Cartesian, like how do we calculate without Cartesian coordinates. And it actually has a lot to do with the Hodge duality. And so if it's helpful to calculate, let's let sigma equal to a dx plus b dy. And all right, so let's just do an example here to start with. And then the Hodge dual of that, right, would have been, according to the rule I laid out last time, let's see, the thing that's dual to dx was dy wedge dz, right? And the thing that was dual to dy is, goodness, dz wedge dx, I believe. All right? And let's study what happens when we take the wedge product of sigma with the Hodge dual of sigma here. What happens? Let's work that out. All right? So we have a dx plus b dy, and we're taking the wedge product with, a dy wedge dz plus b dz wedge dx, right? And, okay, so what do I get? I get a times a, right? A squared dx wedge dy wedge dz. And then notice that when I wedge product x, this piece here, with that piece over there, what do I get? I get 0, right? Because I've got a repeated dx. And likewise, when I take the y and wedge product, two of the wedges here are just trivial. Because I've got a repeated y, see? Okay, but I do have b times b, which is b squared, dy wedge dz wedge dx. And so lo and behold, what we've got is a squared plus b squared, right? dx wedge dy wedge dz. Right? Just to get us warmed up here. Well, we could use what we did last time and maybe do a little bit better than this, right? What would happen if I, suppose sigma is equal to the work form of f. Then what's the Hodge dual of sigma? As I defined it last time, it's the flux form of f, right? So what does that make sigma wedge the Hodge dual of sigma equal to? Sorry, my exceedingly silly turning back of the blank page with your name on it. I'm wasting all of your time. You'll forgive me? Uh-oh. There might have been some spite. All right, so sigma wedge sigma star, what happens here? You got, we got ourselves an omega f vector wedged with the flux form of f. And what did we work out last time? Remember what happened with the work form, the work form wedged the flux form? We had the dot product, right? So this is f dot f times dx wedge dy wedge dz, right? So that's what happens with sigma equal to omega f. What would happen with sigma equal to the flux form of f? It's almost the same story, right? Let's say flux form of G. Flux form of G. Then the Hodge dual of that flux form is the work form of G. And again, we get that sigma wedge, the Hodge dual of sigma, is, well, this time the flux form wedge the work form, which is G dot G, right? times dx wedge dy wedge dz. So apparently, this Hodge dual has something to do with the length of the vector field, right? And so an alternative way to define Hodge duality, which you'd see in like, more sophisticated treatments. So this is why I've said it's a definition. Like an alternative definition of Hodge duality is just this: sigma wedge, the Hodge dual of sigma, right, is equal to the length of sigma squared times dx wedge dy wedge dz. All right. And here I'm introducing a concept which is the length of a form, right? This implicitly defines the Hodge dual of sigma, and where we're introducing the length of sigma as the length of vector corresponding to sigma. So like, for example, the length of the flux form is what? Give me the length of the work form would be what in this way of thinking? Aw, man. My silly thing is problematic. So how about it's just the length of the corresponding vector field, right? So like, does that make sense? I mean, it's a definition, so, and the length of the flux form of G, for example, would just be the length of G, all right? We saw that in example 1, right? In example 1, my vector, my form, a dx plus b dy, that's like corresponding to the vector a comma b, right? And what's the length of the vector a comma b? It's the square root of a squared plus b squared, right? And that's exactly what I had here. I had the length squared of that. All right. Now, it might not seem like I'm doing anything yet, and I guess I haven't done anything yet that much. But now I want to talk to you guys about cylindrical and spherical frames. So I need to introduce yet another definition to be careful here. So definition, if we had alpha equals to alpha 1 dx1 plus alpha 2 dx2 plus alpha 3 dx3, right? And if we had a vector v equal to like v1 x1 hat plus v2 x2 hat plus v3 x3 hat, okay? Then alpha of v is simply equal to like alpha vector dot v vector, where I'm just defining alpha vector to be like, the components of alpha alone, alpha 1, alpha 2, alpha 3. So I'm saying we can take a form and a vector and put them together to kind of get a number, all right? And if we have this concept, then we can introduce what's called the coframe definition. If E1, E2, E3 is an orthonormal frame for R3, then theta 1, theta 2, theta 3 is its coframe if EI acting on theta j. Oopsie, I meant to go the other way around. Oh, that's a typo. Sorry about that, guys. If theta j, rather, goodness. All right, if theta j acting on EI is equal to Kronecker delta ij. What do I mean by an orthonormal frame? We've talked about that before, but let me remind you. Can you give me 3 examples of orthonormal frames on R3? Yeah?
X, Y, Z. X hat, Y hat.
X hat, Y hat, Z hat would be an orthonormal frame, right? What else? You said
Spherical.
the spherical, like rho hat, phi hat, theta hat, right? Or the cylindrical frame, R hat, theta hat, Z hat, right? These are unit vectors that are pairwise perpendicular, right? And the ones I just mentioned are right-handed frames because the cross product of the first 2 is the third, right? So here I'm introducing something new, which is like the concept of differentials that are dual to a given frame. So just to get, oh man, to the point. So let's see here, example 3. If we think about E1 equal to X hat, E2 equals to Y hat, E3 equals to Z hat, right? That's an orthonormal frame. And in that context, we can see that theta 1 is dx, theta 2 is dy, and theta 3 is actually dz. So like, let me kind of expand on that for just a second. So if I think about this as alpha, right? This is alpha is equal to 1 times dx, right? Plus 0 times dy, plus 0 times dz, right? So that shows you that the alpha vector is what? The components of that differential form are simply 1, 0, 0. So like my alpha vector for that is just 1, 0, 0. Yeah? So if I think about, theta 1 acting on a vector, well, I mean not belabor it. That essentially is all I need to. If you sort through the definition I just wrote down, you can see that makes theta 1, theta 2, and theta 3 the coframe to the Cartesian frame. All right, and likewise, example 4. If we look at the frame E1 is, let's say, R hat, E2 is theta hat, and E3 is Z hat, then some calculations can be done, and you can actually prove that theta 1 is dr, theta 2 is r d theta, and theta 3 is dz. So this is the natural coframe. All right. You might recognize those in terms of like our previous discussions about like infinitesimal displacements in the coordinate directions. So there are 2 different ways to derive the coframe. The one would be like sort of through intuitive geometric infinitesimal pictures, and the other is through like the algebra that I'm kind of setting the stage for here, but I'm not really showing you all the details. The details are in the notes in gory detail. I show a method there to derive these things. That's kind of beside the point in here. I'm not going to test you on it or anything. If you find it interesting, like read it and think about it. Ask me questions about it if you want. But if not, it's cool. So the main point is we need to know that the coframe. We need to know that the coframe to the cylindrical frame is this. I don't think that's terribly unnatural, actually. And how about the spherical frame? Spherical frame we'd have E1 is like rho hat, right? E2 is what? Phi hat. E3 is theta hat, right? So you guys tell me what's the, you probably can tell me what's the co-frame to this. Theta 1 is what? Not rho squared. No. Just d rho. Okay, so if I take the infinitesimal geometric approach here for a second, right? This distance is rho. This distance is rho sine phi, right? Phi actually is this angle as well. And so if we do a sweep, right, like this, off the axis, right, then the ds there is just going to be rho d phi, right? On the other hand, if I sweep down there in the xy plane, fixing rho and fixing phi, down here somewhere, whatever, then that ds would just be, rho sine phi d theta, right? If I fix the angles and I just sweep along the rho direction, what's my ds? I know it's hard to see these things, and like here, right? My ds would just be d rho, right? For a little sweep there, where I'm changing rho, but I'm fixing phi and theta. The other one I'm fixing theta, but I'm sweeping through rho. I'm fixing rho and theta, and I'm varying phi for the red. In the green, I'm fixing rho and fixing phi, and I'm varying theta. All right. So those respectively give me theta 1, which is d rho, and theta 2, which is what? I'm not using my color coding here, by the way. Theta 2 is what? Apparently rho d phi, right? And theta 3 is rho sine phi d theta. So now we can think about what is the work form and how do the work form and the flux form correspondences, well, I can't say words. Words are escaping me here. How do the all right. Need to make myself a space. Do over here. All right. Sorry, I've lost track. There was something I was wanting to write down on the board, and I cannot find it. It's bugging me. All right. So the question I want to ask and answer is, what if we have the vector field F, right, equals to, let's say, F rho hat plus F phi hat, right, plus F theta hat. So we've got like the vector field in the spherical coordinate frame, right? Then we can calculate what's the work form corresponding to that, right? So the work form corresponding to that would be like F rho d rho plus Well, okay, so let me step back here for a second. So I do like theta 1, FV theta 2, plus F theta 3, all right? But what are those? We just figured those out, right? So we put those in, and so the form which corresponds here is as F rho d rho plus FV, what was it just rho? Yeah, rho d phi, right? And then plus F theta, I think it was it rho sine phi? Yeah, rho sine phi d theta. All right. Now, oh man, my papers got out of order here, guys. So what I wanted to do all right, so the other thing is we can argue that the Hodge dual of like theta 1 and the Hodge dual of theta 2 and the Hodge dual of theta 3, what are they? Care to guess? So like the structure here is the same as it was for like, let me remind you, the Hodge dual of dx, all right, was like dy wedge dz, right? And so it's the same pattern, actually. It works out so that the Hodge dual of theta 1 is actually theta 2 wedge theta 3, all right? And the Hodge dual of theta 2 is actually theta 3 wedge theta 1. And the Hodge dual of theta 3 is actually theta 1 wedge theta 2. Now, in the spherical basis, what are these? I mean, I have foolishly written them all the way over here, so I have to think, but we've got, so this one gives me rho squared sine phi d phi wedge d theta. This one gives me rho sine phi d theta wedge d rho. And this one gives me rho d phi, excuse me, rho d rho, wedge, sorry, I'm an idiot, d phi. So there you go. Those are the Hodge duals, respectively, of theta 1, theta 2, and theta 3. And basically, if we were to look at the flux form of the vector field, we would naturally define it to be like F rho with essentially theta 1, the Hodge dual of theta 1, all right? My bad. Hodge dual theta 1? Yeah, Hodge dual theta 1. Sorry, I'm thinking here. This is not how I have it written in the notes. I'm thinking through something here on the fly with you guys. F Hodge dual of theta 2. F theta Hodge dual of theta 3. All right, so the formula then for the flux form in spherical coordinates is straight up rho squared, like sine phi, times F rho d phi wedge d theta, plus apparently rho sine phi. It just looks ugly, guys, because I'm writing things in terms of differentials. The coframe makes all of these formulas like much more symmetrical and nice looking, but in terms of calculation, oftentimes we want to work with differentials, so this is worth it, actually. Where was I? Theta, if I haven't made a mistake. All right, so there's my formulas for the, here's my formula for the flux form and also for the work form in spherical coordinates, all right? Okay. Now last time, we worked out how the exterior derivative works, right? And we had like 3 major identities, right? So I want to show you how that plays together with this setup, all right? Let me remind you, major identities. We saw that the differential of f is omega of the gradient of f, right? We saw that the differential of the work form of a vector field is the flux form of the curl of the vector field, right? And we saw that the exterior derivative of the flux form of a vector field is actually the divergence of the vector field times dx wedge dy wedge dz, right? So, all right, some easy pickings here, I think. Example 6. Let's think about the vector field f equals to 1 over rho squared rho hat. Yeah? You guys with me? So what's the work form here? Corresponding. We get work form what? It's just what? 1 over rho squared d rho. You can do differential calculus. You can do calculus at the level of differentials. This is the differential of minus 1 over rho. Right? Because if you differentiate 1 over the reciprocal function, you get minus 1 over the squared function. But then the chain rule says we have to multiply by the differential of the function we're differentiating. And that gets me back to here, right? But on the flip side, this is what? Omega of the gradient of some function, right? I mean, this is, my point is, we also know that, this is omega of the gradient of minus 1 over rho, right? But the thing is, this work form correspondence, you have two work forms of 2 different vector fields are equal if and only if those vector fields are the same vector field. So this constitutes a proof in a somewhat circuitous fashion that the vector field f is in fact the gradient of minus 1 over rho, which was the answer to part A on the quiz this morning. The potential function for the Coulomb field is minus 1 over rho. Right? Now, I asked something that was far less obvious after that. I asked why it was impossible. Why was it impossible to find a vector potential for this Coulomb field on the totality of the sphere? Did anybody find an answer to that? Yeah?
At the origin, wouldn't it be 1 over 0?
Well, but we can think just about a sphere. We don't actually have to touch on the origin. I mean, that's a trouble, but that just means that we can't apply the divergence theorem argument, right? Like, not directly anyway. Anybody else? That's a good idea. I mean, that is part of the issue, the divergence at the origin for sure. By the way, notice that this works on the totality of the domain of the Coulomb field, which is everything in space except for the origin, right? So example 7. So I'll talk more about, I guess I could talk about it now. If you had f, right, is equal to the curl of A on all of R3 without the origin, right? Then what you could do is you could consider, say, the unit sphere, right? Unit sphere. And we have shown this before, that the surface integral, right, over the unit sphere for the Coulomb field is what? It's 4 pi, right? But I could apply, suppose then it's equal to the curl of the vector potential on the totality of the sphere. The sphere doesn't touch the origin, so the origin is not the problem. Not directly, at least. Right? So suppose that you did have a vector potential that was good for the whole sphere. What's the boundary of the sphere? We worked this out the other day in class, right? I explained to you guys that the boundary of a closed surface is empty. So Stokes' theorem applies here. It just applies in a trivial sense as an identity that the the flux of a curl basically is the boundary is empty. It's the empty set, and that makes this equal to 0, which makes this a problem because 4 pi is not 0, right? So there would be a legitimate solution for part B on your surprise attack mission, something like this. This is still, I think, within the grasp of the upper 10% of this class of students who go through here and really understand it. Like, you guys could do that. If you, it's possible students could find this argument, I think. Like, yeah, sure. What I'm about to show you took me years to find. Part C that I just asked you on that quiz at the start of class. Ooh. Well, that's unfortunate. Well, we will just have to remember those things. Part C, I've got stuck on for a while. Let me set the stage for it. Example 8. Let's see if I can do it today. I don't know. Anybody's guess. So we're trying to find f is equal to the curl of A, right? On, most of the, most of R3. I forget what I said in the statement of the quiz, Hopefully I was judicious in my choice of language. Find A for which f is equal to the curl of A on all but a line through the origin. All but a line through the origin, I said. All right? So we can use the word modulo. A line through origin. All right. All right, so I think I've set the stage here. Do we want to use a 1 form or a 2 form to understand this? If you guys have tried to solve the curl equation directly in Cartesians, you've experienced great suffering. Like, I don't know, I can't do, I've not, maybe I could do it if I just set my mind to it. I know it can be done. Knowing something can be done tends to make calculations calculable. But I think we should use a 2 form because we're asking a question about the curl, right? So we need to find out what's the flux form corresponding to, my vector field, same vector field, right? 1 over rho squared rho hat. So we need to go back to the other board and remind ourselves what was the flux form here. What's relevant in the flux form formula for us? Yeah? Look over here. The vector field we're thinking about, it's got no theta, it's got no phi. All we're interested in is this right here, right? So the flux form in spherical coordinates is rho squared sine phi f rho. Rho squared sine phi f rho d phi wedge d theta, right? So the flux form is equal to sine phi d phi wedge d theta. Right? So, can you guys tell me, is this the, oh, come on. Watch out. Would you guys agree with this? This is the differential of minus cosine phi wedge d theta? I hope. And in fact, if you go look at the definition of the differential, like the exterior derivative, this is in fact the differential of like minus cosine phi d theta. Because the way we calculate the exterior derivative of a one form is we take the differential of the coefficient function and then we wedge with the differentials that are there. So that's just definition of the exterior derivative there. But remember that this is what? This is like, this is the exterior derivative of the work form of a particular vector field, which I'm going to call A, right? And that is, of course, the flux form of the curl of A. So this says whatever that A is, we've got F is equal to the curl of A for this A. What is the A? Now we just need to understand how to read. Remember the work form correspondence for the spherical coordinates? What was it? Let me write it in terms of A rather than F. So I've got like A rho, D rho. You guys have to help me out here. A rho, D rho. What was the next one? A what? A phi, is it rho? D phi? Plus A theta, rho sine phi. Did I get it right or did I? So now we just have to play a matching game. As you look at what I have here, right? And you look at what I have down here, what does this tell you that the A must be? We only have a what? We only have a d theta, right? So we have apparently A rho and A phi are both what? 0. And my A theta, well, I can see that A theta times rho sine phi is equal to minus cosine phi. So lo and behold, I get A theta is equal to, you know, minus cosine phi over rho sine phi. And so in short, A equals to minus cosine phi over rho sine phi times theta hat is a vector potential whose curl gives you the Coulomb field. So I've got like one remaining application of differential forms I want to share with you guys. Like I have, it's okay, I got it. I have a derivation of Gauss's law in like 4 dimensions. How would that work out? And that's something I'll show it to you guys like the Monday after break probably. But you know, I'm almost out of differential form stuff to show you guys. I want to show you the formula here. I have something really pretty to share with you, and it fits with this discussion, so we should do it today, and hope you can forgive me if I go a minute over. Come on, computer. So here is the significance of this, guys, is I'm actually looking for the vector potential for what's known as a magnetic monopole. So we found the magnetic monopole potential over there. Here's that calculation I just did in the notes on page whatever this is. And page 422. But what I wanted to show you is like how horrible this is when you go back to Cartesians. See, if you sort back what that looks like in the Cartesian coordinates, putting everything back in terms of x and y's, this is the vector potential you were trying to find in part C in terms of x, y, z coordinates. That's why we couldn't find it. And also, from this, you can see that the line that's missing, which is the line, what line is missing? We talked about this the other day. What x squared plus x squared plus y squared equal to 0 is the z-axis. What makes this particularly perverse is that the z-axis is nowhere to be seen in the vector field F, right? The only deficiency is the origin. Why is the z-axis gone in our answer, right? Well, even better than this, there's a physicist named Dirac, and he found this. This is another way to write A. I don't know how to derive this, but he has rho over z minus rho. So his vector potential is only singular, actually on a ray from the origin, the positive z-axis. This is known as the Dirac string. It's an inevitable consequence of having a magnetic monopole. You have this kind of structure in your vector potential, which is kind of perverse. In the same way that the angle jumps 2 pi as you go around the circle, the solid angle has to jump 4 pi somewhere. That's the significance of this. In some sense, we're looking at the differential of solid angle on a sphere. But anyway, I shut up.